Hello again. Last year we talked about a study that we were working on, and we're still working, but it's just about completed now. And we're basically looking at situations for wintertime tornadoes. When we have what we call high shear, means there's a lot of wind. Low CAPE means it's not real unstable like you'd find, or real hot like you'd find in July. And these kind of events in the lower Ohio Valley. So we wanted to try and nail these things down the best that we can. Well, why? Well, between 2005 and 2013, we had 48 what we call cool season tornadoes. We tend to do okay getting warnings out during the outbreaks themselves, but when there's an isolated event, it's much more difficult. If you break these tornadoes down, they're not strong to violent. Well, some of them are strong, 5 of them out of the 48. 14 of them are considered very weak, but the majority of them are considered, weak tornadoes, but yet they can do some significant damage if it hits your house. If you look at the different types, what do these things look like on reflectivity? They come in all shapes and sizes. Generally, they're in lines. You can see some just stronger storms in lines. You see some that have that S shape, something that we look for, and larger scale S shapes. Inside of these, each one of these, there's a tornado ready to form. And so our job is to figure out which ones and to get the appropriate warnings out. The way we decided to do this is we just looked at the actual tornadoes that had occurred, and then we looked at the environments they occurred in and what the rotation values were prior to the tornado touching down, or even at the time. So we looked at all those tornadoes, again, 48 of them. We didn't look at any false alarms. Okay, we're just looking at when things actually occurred. We then created rotational shear diagrams for each, which I'll look at, and we analyzed the trends. Where's the highest values at? When did it occur? And other general trends we might be able to pull off of the radar data. Well, what about the environment? And what we did here is we combined where, okay, these are the environments that we do well in, the multiple tornado events or the outbreaks where, okay, we get a lot of tornadoes, we do pretty well getting the warnings out. How can we compare that to the isolated events and then try to learn something from there? What can we use in an operational sense? Here's an example of a rotational shear diagram. This is actually from the Pulaski County tornado back in 2005 on January 13th. We had the tornado touch down about 9:05 UTC, which is about 3 in the morning. And we went back, looked at the radar data and say, well, what can we see in a rotational value and heights? And so the values of 30 are in red, blue is the values in the 20s, and I changed other colors if we got into different values. But you can see that here's our rotation. It tends to deepen, and right before the tornado occurred, we had some increase into the lower 30s. So if we see this type of trend continue in the other tornadoes, hey, that's something that the forecasters can look at, things that we can key in on to try and get warnings out for these types of things. These values are much lower than you get for typical supercells, so you have to be ready for this kind of situation. How about during an outbreak? Well, here's an example where one circulation produced 6 tornadoes and a microburst. Okay, it moved across Bollinger, Cape, and actually into Alexander County in Illinois, and you see the values are coming down. Well, here as they are getting closer to the radar. The values are not very strong when we get our first couple tornado reports, values in the 20s. And then they start to seem to increase right before the microburst and the tornado. But then they really start to increase. See some 40s way up there, about 6,000 feet prior to this tornado. And as we look at this tornado, the last one here at 56, we're looking at some values of 35, 33, but notice that the highest values are not in the lowest slice. So you can't just look at 0.5 on your phone or 0.5 on the radar data that you might get on the internet and say, well, it's not any stronger than that. It could be. And so you don't want to just use the 0.5. You always want to look at things in a volume context. So what do we find from the circulations? Well, we found that the strongest rotation, if you average all the volume scans together, the height was about 6,000 feet up. So again, you just can't look at 0.5. You're likely going to miss the highest value, and we warn off of what we see the highest values. How often was it in the first volume scan at or prior to tornado genesis? Really less than 50% of the time. What that means is that if the highest value is not right when the tornado occurs and it's before then maybe we can put together and get enough information to say when we see this value, we should issue tornado warnings, and the probability of getting one is relatively, hopefully, high. We also notice that the EF scale does not seem to be connected to the maximum rotation that we see. But remember that we're looking at rotations up to and at the time of tornado, not when the tornado's on the ground. What else did we find? Well, we found that 38 out of the 48 cases, we could trace the circulation back at least 4 volume scans prior to the tornado. So that's looking at anywhere from 12 to 15, 20 minutes before the tornado occurred, there was sign of circulation. Remember, again, most storms rotate, but it's the degree of the rotation that's important and the depth of the rotation. We also looked at spectrum width, which is not a common thing that people use. We're finding it more and more useful. And 46 out of the 48 events had values at or above 20 knots prior to or at the time of tornado formation. We just looked at the lowest couple slices there to try and limit the amount of data that we're getting from this study. So if we looked at the median values from different ranges, okay, in the 0 to 29 nautical mile range, we had 18 tornadoes. And we looked at basic values around 29 to 30 knots was the median prior to or at tornado time. Going out 30 to 59 nautical miles, you're looking at 25 to 28 knots. Beyond that, 26 to 30. So we're hovering in the upper 20s to around 30 knots. It seems to be a very consistent value no matter where we are in the range from the radar. So when we're in these type of environments, which we'll discuss in a minute, and we're seeing this type of rotational value, and it's consistent, it has depth to it, it's been there for a couple volume scans, then we need to strongly consider issuing tornado warnings. And this doesn't matter whether we're in multiple, an outbreak type situation, or maybe even, and the most difficult thing is when there's just an isolated storm. Do we issue a tornado warning in these types of environments? And so that's what we're trying to get from this study. So what do we find out about the environment? To do this, we considered each tornado an event. So when there's an outbreak, the environment's relatively similar, so those are going to be have a stronger bias in the study. What we found was the most unstable CAPE to be the most consistent instability parameter, meaning it had a value prior to every tornado. If we use mixed layer CAPE, it was actually 0 prior to one event, so that's not going to help you. If you look at surface-based instability, it was 0 for 7 of the events, so you really don't want to use surface-based CAPE to try and determine beforehand, and even up to tornado time, that you have enough instability to produce the tornado. You may have the shear, but you have to have some instability, which is, again, warm air rising. So the median value of the most unstable CAPE was about 600, okay? What would you get for a typical supercell? Typical supercell environment, you're looking at, 2,500. So that's how much smaller scale these things are. So we decided then to look at the shear. The shear is a change in wind speed and direction with height. And here we're looking between the surface and 1 kilometer. Well, that made up 80% of the 0 to 3 kilometer shear. So that's probably a better one to look at. And the median value, a lot of times you look between 35 and 40 knots as being your key values, and we got the same there. Storm relative velocity is about 235, but they definitely range all over the place. I'll show you that. But we also looked at 0 to 6 kilometer shear, which is 0 to about 20,000 feet, and that seemed to actually be a good discriminator between isolated and our multiple or outbreak events. What kind of temperatures and dew points? Well, we've always told you that when you see dew points getting into the upper 50s, that you really need to be concerned in the wintertime. And this shows it out. Now the median values are a little bit higher, 68 degrees, and dew point is 62. But again, that's going to be a range. That's not the full value. One of the surprising things was that it was a very moist environment. All but one event had values of precipitable water greater than 1 inch, which is above the 99% percentile for December through March. So it's way above what it normally should be. So let's look at some more findings from the environmental data that we had. And that was shared to us from SPC. So we're looking at isolated events. There are only 7 out of the 48 were considered isolated. I mean, there wasn't another tornado for a couple hundred miles. Multiple events means we had more than one tornado within 100 miles. These box and whisker plots, basically, the bottom of the box is a 25th percentile. The top of the box is 75. So you're looking at 50% of the data is going to be in the box. The bottom whisker is the bottom down to 10%, and the top is top up to 90%. The thick value in the middle is the median. And so what we look for is can we find a discriminator? I mean, is there a significant difference between these two? In 0 to 1 bulk shears, the mean values are right around 40 knots. There's not a lot of difference in the data. When we look at 0 to 3 kilometers, again, this box almost fits inside that one, so our values are a little bit higher, probably in the low to mid 40s. Now, when we looked at 0 to 6, which is again 0 to about 20,000 feet, on the isolated events, it was at 60 as the median, but in the multiple events, the median was well into the 70s, if not 80. And this box and this box have very little overlap, so we might be finding something here. This is the first one that says, hey, this might be important, but we don't have it's not a whole lot of data. It's very preliminary. How about CAPE? We talked about this again. The isolated means the 7 isolated events. And if you're looking at surface base, again, a lot of the values were very low. And so you really don't want to use that. Mixed layer CAPE, it was pretty decent and had values for all but one of the cases. But when we use the most unstable, we can see we have a wide range, but we have values prior to the tornado touchdown. So if you're looking 3 or 4 days out and you got a system that's moving at you and you think, well, we may get some storms with this. If you look at surface-based CAPE, it may say 0 and you still might get storms. You look at mixed layer, you may look at that and say, well, the values are still near 0, so I'm not too worried about it. What is the most unstable CAPE show? That might be a better key to help you with that. When you're looking for these circulations, again, I talked about them, they're relatively weak compared to looking at a supercell storm that you'd see in the spring or summer. But colors are key whenever you're looking at something to try and say, hey, there's circulation there, I need to worry about it. This is something that's a concern. So looking at the GR Analyst program, here's can you find the circulation in this? And would it be considered significant to you if you found it? I don't see anything that's just sticking out of my mind. Well, let's try another common color scale that's used across the Weather Service. And okay, well, something's showing up here, but I've got very little outbounds. I got some greens there, so there might be something in that area, but it certainly doesn't. It's not jumping out at me. Well, what if we change the color scale even more? Now you've got blues and you've got reds. Here's our circulation. And yes, there was a tornado in and around this time, southwest of Poplar Bluff. So colors are key. You need to know what the colors are going to be. You have to use the right color scale in order to pick out the feature that you're looking for. So what are the operational considerations when we have these things, especially for isolated tornadoes? Isolated events, vigilance is the key. You have to watch and have to watch and have to watch. You just can't look at the 0.5 and assume you're seeing everything you need to see. Forecasters cannot lean on lightning. We had a couple of these events, at least one of them for sure, where no lightning was detected at all. The tornado that went through Mayfield in October a couple years ago, no lightning. So there's nothing for people to even key on that, oh, it's just raining, it's no big deal. You can't always count on the Storm Prediction Center having some type of a watch or something like that out because it's just one tornado. They're looking for the larger areas. We're expected to take care of these little things. And even your typical severe weather parameters like storm, surface-based CAPE and maybe mixed layer CAPE, those are not the parameters to look at. So in these type of environments, even the large area showers, we must look for these small lines, 40 to 50 dBz echoes, and say, I need to focus on this and put other things aside. So thank you so much for your time.